So this is 10.4. This is problem 2, and in the very first ones, in 10.4, they want you to do the straight comparison, which is harder to do than the limit comparison, because you actually have to play games with inequalities if you're doing it right. So you want eventually to compare this fraction with some other fraction which corresponds to the general term of a series where you know what it does. And if you notice that what I do, I end up showing that this fraction is less than 1 over n cubed. And 1 over n cubed is a series, is a p-series. Remember, we did the p-series 1 over n square and said it converges. And if you had 1 over n cubed, you could do the same kind of thing. You could use the integral test to prove it's convergent, or you could simply say, I know it's a p-series, p equals 3, and so on. So the game here is comparing this with 1 over n cubed. So you remember that if you make with fractions, start out looking at the denominator. So this is certainly more than that, because it's 2 more. Okay, so say that's obvious. So then 1 over the bigger number is less than 1 over the smaller number. This is the larger, smaller, so 1 over larger is less than 1 over smaller. Also, I can compare the denominator here with a smaller denominator, so I can think of it that I took n minus 1 times 1 over n squared, n fourth plus 2, and that would be less than if I took n minus 1 times 1 over n fourth, because that's bigger. On the other hand, the n minus 1 is certainly less than n. It's 1 less. So my fraction here is less than the one where I take the n minus 1 times a bigger factor, 1 over n fourth, and then that in turn is less than n, and the same denominator. So this is less than that, is less than that, which is 1 over n cubed. So if this converges, that does, because it's smaller, term by term. This is a p-series with p greater than 1, so it converges, so the smaller one does. The inequalities go through all right, it's just that it's hard to say it, kind of. But what I have done is essentially to say that n minus 1 is less than n, and that what I've multiplied here, 1 over n fourth, is more than what I've multiplied here. And so put together, this fraction's less than that one. There's a rule here as to how, with problems like this that are where the general term is the quotient is a polynomial. Problems like this that are like quotients of polynomials are like what you call rational functions in Math 143, ratios of polynomials. And the game that you play when you have a rational function type general term in your series, to find a comparison series is you take the quotient of the leading terms, the highest powered terms in your polynomials. So that's n over n fourth, and that gets you the 1 over n cubed. So the best comparison series that you could probably use here is the 1 over n cubed. So you do algebra like the Math 25 people want to do algebra. So you forget about the -1, forget about the 2 here, and just look at n over n fourth. Because when you're talking big numbers and limits, the n dominates here, and the n fourth certainly dominates there. There's, if you think of it, say, if you thought of n as 10, this as it is would be 9 over 10,002, okay? 9 over 10,002 and 10 over 10,000, there's not that much difference. If you try it on your calculator, you're talking 1 to 1,000, right? So that the dominant numbers are the n and the n fourth, which is like 1 over n cubed, 1 over 1,000. So you could take your calculator if you want to do 9 over 10,002 and compare that with 1 over 1,000, and you'll see there's not a whole lot of difference. So that's how you get your comparison series. Let's see where this is. Then we skip over to here. Let's see. We talked about, so take a look at this one then. This is a comparison or limit comparison test problem. This is 10.4, number 9. And so based on what I was saying, you look at the leading term in this polynomial, n, divided by the leading term in this polynomial, n cubed, and n over n cubed is 1 over n squared, which you know is convergent. We proved that down there in the corner. That's a p-series with p equals 2, and we really did it as an integral test. Okay, so that converges. So the limit comparison test, remember that's here. You want to compare the a's with the b's, and the b's in the denominator, that's the series where you know what it does. So if your limit is a positive constant, they behave alike, or if this limit is 0, then the if this limit is 0 and this one converges, then that one converges. And if this denominator limit series has a limit that's infinite, then the numerator series diverges. So in this case, our if we set up the quotient, so this is the ANs and this is the BNs, so take the limit of this quotient, so invert and multiply. So you have n squared times n minus 2, which is this, and then this denominator is here. Okay, that limit is 1, which is positive. How do I know this limit is 1? Well, you could replace the n with x and use L'Hopital's rule and do the derivatives until you get down to constants. Or you could divide by n cubed. This is Math 143, Math 147, how to do rational functions. Divide everything by the highest power in the denominator, and then use the fact that 1 over x, 1 over x squared, and so on all go to 0. So if you divided by n cubed, you'd have 1, then 2 over n, 1, 1 over n, and 3 over n cubed, and you'd have 1. So the test series and the comparison series both converge, because the 1 over n squared, that is your comparison series, converges. So let's finish with some examples of ratio and nth root test. And as I said earlier this morning, when you have series involving n factorial, you're almost always going to use one or the other of these tests, because you can't integrate the n factorial and you can't differentiate. So one of the things, if you look at our various handouts on some handy formulas we have, 1 over the nth root of n factorial in the limit is 0, and the limit itself of the nth root of n factorial is infinite. Those are handy things to know in working with either the ratio or nth root tests. So if you look at problem 1, you have 2 to the nth over n factorial. And if you want to do it as a ratio test, then you take the limiting ratio of your n plus first term, which would be this formula with n made into n plus 1, divided by the nth term, which is this formula as it's given. So the formula that's given is the u sub n in the book, and the formula with n made into n plus 1 is u sub n plus 1. So then invert and multiply, and you have n factorial from here. The 2 to the n plus 1 is 2 to the n times 2, factor it. Then on the bottom you have the 2 to the n, that's this one, and then the n plus 1 factorial is n plus 1 times n factorial. See, for example, if n were 3, n plus 1 is 4, and 4 factorial is 4 times 321, which is 3 factorial. So it's a handy fact about factorials that n plus 1 times n factorial is n plus 1 factorial. So then cancel like things, and it leaves you 2 over n plus 1, and that limit is certainly 0. And if your limit is less than 1, where did the ratio test go? Rho less than 1 means the series converges. And that includes rho equals 0, which is certainly less than 1. So you can prove this thing converges with the ratio test. If you have these limits available, you can also do the nth root test. Limit of the nth root, then, of your general term would be the nth root of 2 to the n, which is 2, and the nth root, and it's 2 times then the limit as n goes to infinity of 1 over the nth root of n factorial, and that limit is 0. So your limit of your product is the limit of 2 times 0, which is 0. Same row and same conclusion. See, your row here out of the ratio test is 0 in the limit. The row here out of the nth root test is rho equals 0 in the limit. Same conclusion. Always the ratio test and the nth root test both fail if rho is 1. They both say divergence or they both say convergence. Okay, let's look at 15, which is kind of interesting, and I have a handout that goes with it. 15, as the maple says, and so you see what I've defined for my F is the general term here in the series, and then what I'm calling points is the set of values for the sequence n f nth root of f of n from 1 to 6. See, I'm thinking about an nth root test by taking the nth root of what I'm calling f of n, which is my general term. And so you see the values, if you don't do EVALF, you'll get all these numbers that you can't really make any sense out of much. So you notice I went to EVALF, so then you get the nth roots as decimals, and you have a sequence then. First I went through 6 of them, then 10. You notice that the sequence of nth roots by the time I get up to 10 is has a value 3, 4, 8, 6. Notice that then I asked for the value of e to the minus 1. So you notice that the number in 5, line 5, is not exactly the same as the last thing in the sequence in line 4, but they're not too far apart. Then if you take the sequence and go to 100, goes on and on and on, and you turn the page, see, it goes on into the night. But take a look at the last one there. When n is 100, your value, your nth root, and remember it's the nth root of this, your last value is 0.3660, and the value of 1 over e back on the previous page, line 5, is 0.3678. So this is experimental evidence that this sequence of values is apparently going to 1 over e. And you would expect then 1 over e is what we're going to get to. And then that, as our limiting value, is less than 1, so that in turn would prove convergence. You see, you're trying to prove convergence of the series here if you're taking the nth root test by setting up the sequence of values for these nth roots and then showing that the limit of that sequence is something less than 1. And what my data indicates is that the limit of the sequence is actually 1 over e. So notice first of all that n squared is n times n. And so you could take one of the n's and put it with the 1 minus 1 over n, like this, and then the other one is out here. And then if you're going to test for the limit of the sequence of nth roots, you're taking the nth roots of this thing. So this n will cancel with that one. And it'll leave you then that the sequence that you're trying to show the limit of is less than 1 is the sequence 1 minus 1 over n to the nth. And if you want to do it by algebra, you can say that n is minus n times minus 1, and then if you set this equal to x, minus 1 over n will be plus 1 over x. So then this thing becomes the limit as x becomes infinite of 1 plus 1 over x to the x. And then this minus 1 is this one. Okay, that limit is e. So what you have is limit here, which is e to the minus 1 power. So 1 over e. And 1 over e is less than 1, so the original series converges. So I'm not saying that the sum of the series is 1 over e. I'm saying that if I'm doing the nth root test, I'm taking the limit of the sequence of nth roots, and that sequence of nth roots limit is what's 1 over e, which is less than 1, and all that proves is that the series converges. It doesn't say this number is the sum of the series. So look again at your Maple handout. You see on the second sheet of paper I have the picture of the terms in the sequence for the first 6 terms, and they're approaching a horizontal asymptote, which is the value of which is the 1 over e, the 0.36. And then if you turn the page, it's the same picture really, except that I put the horizontal asymptote in there in red. So you can see that you have dots in sequence that might believably be approaching the horizontal line at the top of the page as their limit. And to see that they most likely really do, you have to go back to the numbers where I took the sequence out to 100. You can see that's too much to try and draw. So then, last one for today is problem 19, where you have n factorial e to the minus n, which you can write this way. And if you do it as a ratio test, your n plus first term is n plus 1 factorial, e to the n plus 1, and then your nth term, you copy what you have. And then simplify your fraction and rewrite your n plus 1 factorial as n plus 1 times n factorial. It cancels that. And write this as e times e to the n and cancel that. So your ratio is n plus 1 over e, and you can see that limit would be infinite because the n is the variable and it's on top. And so what you have is infinity, which is greater than 1 for your ratio test. Rho greater than 1, that includes infinity. So you have divergent series. You can also do it as an nth root test because you get the nth root of n factorial on top and e on the bottom, and that's an infinite limit. Again, I said that two handy recipes to be sure you have is that this limit 1 over nth root n factorial is 0, and the nth root n factorial itself then is infinite. Well, what we'll do tomorrow, we'll talk about alternating series and start talking about power series, which would be the next two sections. And remember, next week I will be giving out the 4th test, and it involves some work with series. I've been trying hard to get far enough so that you can do the questions that are on it. And it also involves work back with the problems like area and arc length in polar coordinates, some of the things that we did before spring break that we haven't covered on the test. So let's look at doing some of the problems. Look at problem 1, for example. Now this is actually a p-series, so if you see it as a p-series and have learned that the p-series converges for p, remember, is the exponent. So it's a p-series with p equal 2, which is greater than 1, so it is convergent. But you could show that with the integral test. So if you were doing this as an integral test, change the n into a continuous variable x, and think of f of x then, 1 over x squared. So to use the integral test, the f of x has to be a decreasing function from some point on. Well, 1 over x squared is, you see, how the graph looks. And typically your series starts at n equal 1, so what you really care about is it's decreasing from there on, but actually it is for positive x. And then you do the improper integral, limit as b becomes infinite, integral 1 to b of this as a function of x. So you add 1 and divide by the new exponent, and I'd factor the minus sign out and take the limit then of 1 over b from 1 to b, limit as b becomes infinite, so then you have the minus, this limit, which is 0, and then that's a minus 1. So then you finally have minus 1, so the integral converges. So therefore, the series converges. Because, again, back here, what we have is that the sum of all but the first term of your series is less than or equal to your improper integral. And then if you add the first term on, the whole thing is greater than or equal to your improper integral. So if this value is 1, which is what we got for the improper integral, what we know is that the first term of this, which is 1, plus the improper integral is greater than or equal to the sum of the series. In other words, what you know is that the sum of the series is greater than or equal to 1, which is this improper integral, and the series is less than or equal to the first term plus this integral. This is 1 and that's 1, so the sum, 1 over n squared, is somewhere between 1 and 2. And if you wanted to, you could then use this idea and talk about using the first 5 terms or the first 10 terms and get an estimate on how close using the first 5 or 10 terms would take you to the true sum of the series. They don't ask you to do all that, but you could. So, in the same way, look at problem 6. See, my conclusion here on the p-series, for example, is that the first 4 terms, which would be 1 plus a quarter plus a ninth plus a 16th, would be between 1 and 2, something like that. And you can kind of see that it's so. It's certainly more than 1. And these, a quarter plus a ninth plus a 16th, are not going to add up very fast. So it would take a lot of terms to get close to 2. The actual sum then may not really be as much as 2. I'm sure it isn't. I don't know exactly what it is, although it's probably something which is actually known in mathematics. Well, take a look at problem 6, where we have 1 over n log n, the quantity squared. Now notice that's not n squared, it's log n times log n. You take n, then you take the logarithm, and then you square the logarithm, is what that means. So, if you think of the related function of a continuous variable, that would be f of x equals 1 over x log x quantity squared. Remember again, a continuous variable means that it takes all values, the values of all real numbers in any interval you want to talk about, whereas the n is just 1, 2, 3. So it's the functions of continuous variables that you can integrate and differentiate. So if you think of that function, the first thing you want to prove is that the thing is decreasing, at least from some point on. So that's what I've done down here. If this is f of x, I'm doing the derivative, and you remember with your quotient rule, it's the denominator times, which is your x log square, times the derivative of the numerator, which is 0, minus your numerator, which is 1, derivative of the denominator, which is product rule, as my sign warns you, all over the denominator square, right? Or if you prefer, if you want to think you're in Math 160, the business school types can't remember the denominator times the derivative of the numerator. So what you have to do to teach them is you say this is high and this is ho, and then this is ho-de high minus high-de ho over ho-ho, especially if it's close to Christmas time. Then you can say ho-ho-ho, right? Anyway, so much smart mouth. That's 0. Then you do your product rule. So derivative of x is 1 times log square plus the x, and then bring the 2 down, log x, and then the derivative of log is 1 over x. Notice those x's cancel. And so you have minus log square plus 2 log x on top, and then you have x square, denominator square, log square square, so log fourth. And then you see that log is a factor there, and it'll cancel with one of those. So your f prime looks like this. And the minus sign is important. See, that's because it's denominator times the derivative of the numerator minus numerator times derivative of denominator. So your f prime is minus stuff that is positive. For x greater than 1, your log is positive, and certainly for x greater than 1, your x is positive. So you have minus something positive, so it's negative. So your function's decreasing. Notice this series starts at 2. You could not have it start at 1 because log of 1 is 0. So this is from 2 on. And you're made as a function of x, your general term is then decreasing, so it meets the requirements that you can test the convergence or divergence by doing the improper integral of f of x, say from the starting point from 2 to infinity. Okay, so to do the integration, now you want to do u substitution. So if u is log x, so you're going to integrate this thing, then your du is 1 over x, and which I have here. U is log x, then du is dx over x, and then if you're doing the integral from 2 to infinity of 1 over x log square, you, as a definite integral, you want to change your limits to limits on u. So if u is log x and x is 2, then u would be log 2. So that would be your lower limit. And if, as x goes to infinity, log goes to infinity. So your improper integral then, in terms of u, is log 2 to infinity, u to the minus 2 du. So you know what to do. Add 1, divide by the new exponent, and then take your limit. So this minus is out here. This is 1 over u. Limit as b becomes infinite, 1 over u from log 2 to b. Well, your upper limit, 1 over b will go to 0, and so you'll have minus 0 minus log 2, so 1 over log 2. So you do get a positive number, so the thing does converge. So series converges. So this is an example of using the integral test for a series where it isn't at all obvious whether the thing would converge or diverge. Look at problem 33. This is also in 10.3. So you have n sine 1 over n. Now remember that the first thing on your summary sheet of methods to use for testing for convergence or divergence is the nth term test, where if the limit of your general term is not 0, it diverges, period, end of story. Okay, so do that one here. You can rewrite this as the sine divided by 1 over n, see, because if you take this and divide fractions, you invert and multiply, and that would be what you started with. And then call this t. So you have sine t over t. So if you have t equals 1 over n, then take the limit as n becomes infinite, the original limit you're going to take, and find what this becomes, say 0, then the limit of your fraction with the original variable, as that one goes to infinity, equals the limit of the new fraction with the new variable as that one goes to whatever limit you got here. So it's the same as the limit of this fraction as t goes to 0, and that from Math 170 is 1. In chapter 3, one of the very first limits they prove in the book, they prove it geometrically there, is that sine t over t is 1 in radians. For this limit to be 1, you have to be in radians, and that's really why you use radians in calculus, so that the derivative of the sine will be the cosine. If you use degrees, you'll have pi over 180 every time you open your mouth on what the derivative is. And you could also use L'Hopital's rule. You see this gives you 1. As you do the derivatives, you get cosine of 0 over 1, and cosine of 0 is 1. So the nth term does not go to 0, so the series diverges. So they have this problem in here in the section that's focused on the integral test, basically to keep you honest, you see. So, just better hand out my sheets here. Just a second. The P series, you remember, converges if P is greater than 1, so something like 1 over n squared, for example, is convergent, and it diverges if P is less than or equal to 1. When P is 1, that was the harmonic series. If you were here last week, you remember I showed you the first way that people proved that 1 plus a half plus a third plus a fourth diverged. I had the fractions clear across the top of the board there, and we could group the fractions and say a third plus a quarter was more than a half, and then a fifth plus a sixth plus a seventh plus an eighth was more than a half. 2 quarters, 4/8, 8/16, and so on like that. So you can use the harmonic series as a comparison series if you're proving divergence, or the series like 1 over n squared or 1 over n cubed to prove convergence, perhaps, or you can use geometric series. These are the standard comparison series to work with. And then we also have the ratio and nth root tests. So the ratio test, we assume that the an is a positive term series and take the limiting ratio of the n plus first term over the nth term. And suppose that comes out to be Greek letter rho. That's what the book uses. If rho is less than 1, you have convergence. If rho is greater than 1, you have divergence, which is great the problem is the test fails if rho equals 1. If you take the harmonic series, the sum of 1 over n, that thing will give you 1 for the ratio test. So you don't learn that way whether that's convergent or divergent. In fact, the ratio test will give you 1 for any p-series, and some of them converge and some diverge. Nevertheless, this is very valuable, and it's generally how you go about things if you have factorials. The alternative to this is called the nth root test, and you take the limit of the nth root of your general term. The rho you get here will be the same value as the rho you get here for any one given series. So the nth root test and the ratio test are equivalent, really, for series. So they both fail. If one of them fails, the other one fails. They both tell you it converges, or they both tell you it diverges. And the rho value will be the same number. So the limit here is rho, which is the same as the rho that you get from the ratio test limit. So they both give you the same conclusion. They never contradict each other, and if your test fails one way, there's no use trying it the other way, assuming you did it right, of course. So proving the ratio and nth root test is based on a comparison of a sequence of ratios or of nth root values with the common ratio of a related geometric sequence where the common ratio is less than 1 if it's convergent, or greater than 1 if it's divergent. So the sequence of ratios or of nth roots converges or diverges the same way because it's the same proof. So they either both work or they both fail. You never have contradictory results comparing ratio and nth root tests. When one fails, so will the other. Okay, well, let's do some examples here. Now, what I've reached at this point is the rundown of the methods that are in your book for testing convergence or divergence of a positive term series. So if you think of a long sheet of paper with a summary of recipes, I think everybody has it, but let me this. I'll give you another one.
I think I got it, but thanks.
Everybody, okay.
I got it.
Well,
Thank you.
Okay, good. So, you see how these tests are listed here. So, the first thing you do is the nth term test, because if your nth term limit is not 0, it diverges. Okay? But that's all that proves. It doesn't prove convergence. Then you have the comparison test and limit comparison test. Then you have the integral test. You have the ratio test, and this book, and then you have the nth root test. So those are the ones that apply for positive term series. What we will talk about tomorrow, we'll talk about what are called alternating series, which go plus, minus, or else minus, plus, minus, plus. And tomorrow we'll also start talking about power series, which is the whole point of the chapter really, because the power series are the ones that you use to compute the values of sine and cosine and log and so on. So we have completed putting on the board anyway the different kinds of tests that go with positive term series that are covered in a standard calculus book. There are other tests out there that are kind of special case tests that you would see if you took more math, but they're not normally presented in a class like this. Sure they have these. And so let's pick up with that, which is in here. So again, the integral test for convergence or divergence requires basically that we can integrate a function of a continuous variable x that's made in the same form as the general term of the series. So we think of the general term an in our series as f of x for a continuous variable x. Continuous variable means x could be any real number. So it's all the decimal numbers, fractions and not, whereas when we're talking sequence, our variable is 1, 2, 3, and so on. So those are the functions of a continuous variable are the type that we are using when we're doing integration. And if they're continuous, you can always do an integral, and you can also do integrals if they're not too badly discontinuous. So then our theorem from last week is that as a function of a continuous variable, if the general term of your series is decreasing for all values from some point onward, it doesn't necessarily have to be for all x, but say for all x greater than or equal to 2 or 20 or something. Remember that the first 20 terms, or 200 terms, or even 2 million terms of a series aren't what determine convergence or divergence, because that's still a finite sum, even if it's a lot of terms. So convergence or divergence is from this point on forever, yes or no. So to apply the theorem then, it could be that you're working with a series where at first the terms are increasing, but they have to start decreasing and keep decreasing from some point on. Well, if you meet these conditions, then if you were here last week, you remember I had drawings with the curve and with the rectangles, and there were rectangles where the tops were above the curve and rectangles where the tops were below the curve. And so what we have is that the integral of our function of a continuous variable from 1 or wherever it is you're starting to infinity. First of all, we're if thinking of this as an improper integral, which means it might converge or it might diverge. The integral will be greater than or equal to the sum of the terms all but the first term. Notice this is starting with 2. So, and if you put on the first term onto this so that you have the total series, that'll be greater than or equal to this integral. we went through that last week with our pictures on Friday. So that means if this converges, so it's a number, then you could add the first term to this and have the whole series. So the whole series is then less than or equal to the first term of the series plus this. So that means it's less than or equal to a finite number if this is finite, if it converges. On the other hand, if this diverges, so this is infinite, the entire series, including the first term, is more, so then it's divergent. So the series then converges or diverges if and only if this converges or diverges as an improper integral. Remember, converges means it's a number, and diverges means it's infinite. We're assuming that this thing, these are positive term series, so this is a positive valued function, so this is a positive number, or it's infinite. So the integral converges as an improper integral. Remember that improper integrals and the idea they converge or diverge is at the end of chapter 8 in Math 170, which we did in Math 175, if you remember. So the integral converges means the series does. The integral diverges means the series does. Well, we also can use the integral, assuming that we have a convergent series, we can use the integral to tell us how close we are to the true sum of the series if we take the first n terms of it. How many terms then are good enough, that sort of thing. So suppose S is the true sum of the series, and then S sub n is the partial sum of the AKs, A1 plus A2, from 1 through n. So the remainder then, if you've approximated your total, this number, with this partial sum, is what we call R subscript n. I'm using the symbols that are in the book. And so R sub n then is the true sum, capital S, minus the partial sum. So thinking of this as the error in using S sub n instead of capital S, we're thinking error is true minus computed. That depends on whose book you're in, but either this or computed minus true is going to be the error, and it depends on which way you define things. So this is how your book has it, and it's as good as any. So then what we have is that the remainder or error, if you have used the partial sum of n terms for your actual sum of the series, is between this integral and that one. These would be numbers. Remember, we're thinking of the f of x as a positive valued function, and we're thinking of it, it's a convergent series, so that means that the integral 1 to infinity converges, so then the integrals n to infinity or n plus 1 would converge. So this will give you a number, and that'll give you a number, and your error is between those numbers. You won't know it exactly unless you actually get the true sum of the series. But you could say that the error is between 1 in 1,000 perhaps, and 1 in 10,000, something like that. If you really want to take enough terms, if it's important. Well, of course, if you're trying to build something, then computing numbers is important. And so this is sometimes really useful. So you can use the integral from n to infinity to estimate how many terms would be close enough. You might find that 5 terms will make an error that's between, say, 1 in 1,000 and 1 in 10,000, and perhaps that's enough. So the problem with using the integral test is that many series involve the factorial. For example, something like this. Here's a series. If you looked at the corresponding function of a continuous variable x, which would look like that, how would you integrate something like that? Well, the answer is you can't, because we don't know how to integrate factorials. You can look through your book in vain and you don't see how to do that. So there are a lot of series where the integral test won't work because you can't integrate it. Yeah.
Did factorials come from a previous math class? I don't remember.
Well, they talk about factorials in Math 143.
Okay.
You know, and I would think that there are some places in Math 147 where people would work with factorials.
That symbol's not Boolean? I'm sure, right?
That symbol is
that's not a not symbol. It's not Boolean.
No.
I'm sorry, I didn't mean to interrupt.
Well, I was trying to think where we can write. Okay. So the two main things about the factorial, the reason for the name, factors are things that you multiply.
Okay.
Okay. So it applies for 0 and for positive whole numbers.
Okay.
1 factorial, 2 factorial, 3 factorial. And so whatever this number is here, it's the product of that number, the next one down, the next one down after that, and so on down to 1.
Oh, okay.
So, for example, 4 factorial
Oh, okay. It's starting to come back.
is 4, 3, 2, 1. So that's 24. I put dots in for multiplying. 3 factorial so 1 factorial is 1 and 0 factorial by definition is 1 so that you can make various formulas work all right, that involve the factorial symbol. So this is 24, and this is 6, and this is 2.
Okay.
It's a key on most calculators, I think. If you have a student scientific calculator, I'm sure there's a factorial key on it.
Okay.
One way or another. And a lot of series use the factorial as part of the formula for the general term, like in my example here. And we don't have a way to integrate the corresponding function as it would be if you changed the n into an x. The problem is that the factorial is defined for 0 and positive whole numbers, so going from here to there is something that's not defined. It doesn't really make sense, so you can't do it. So you can't use the integral test for series that involve the factorial as part of the general formula. So what can we do? Well, we have in section 10.4 the two forms of a comparison test. We have the comparison test and we have the limit comparison test. And the limit comparison test is easier to use as a rule. So the theorems look like this. This is the series where you want to decide converge or diverge. And the book uses C and D for converges and D for diverges. So what you're going to do is either compare the test series, which is the A, is the one where you want to know where you're testing, what does it do, converge or diverge. You're either going to compare it with a series where you know it converges, or you're going to compare it with a series where you know it diverges. And it takes a certain amount of experience and intuition to get going in the right direction. If your series actually does converge, this one, the one you're testing, then what you want to do is compare it with a series where you know this comparison series converges, and then you want to prove that this is less, the terms are an are less than or equal to cn from some point on. On the other hand, if this thing diverges, you want to compare it with a series where you know it diverges and show that the ANs are greater than or equal to the DNs for all terms from some point on. And so it takes some correct intuition to make the comparison with the correct series here. If this thing diverges, you're not going to ever get anywhere trying to show the terms are less than or equal to those in a convergent series. And if this thing converges, you're not going to get anywhere comparing it with a divergent series. So you got to make the right choice, and that's sometimes hard to do, but that's the game. It's easier instead of a direct comparison, which requires working with inequalities, which are always hard for people. It's easier to do the limit comparison test, where if you have positive term series, AN and BN, and if the limit of the quotient is a positive constant, then the two series behave the same way. The series you're testing and your comparison series, they either both converge or they both diverge. It's generally easier to take a limit of a quotient like this because if it doesn't involve factorials, you can do L'Hopital's rule. Another thing about factorials, you cannot integrate them, and you also can't do their derivatives. So that's So if also on the limit comparison test, if you have a limit which is 0, and if the comparison series where the one where you know what it does, if it's convergent, then the test series, the A's, converges. And finally, if your limit is infinite and your your comparison series diverges, then your test series diverges also. So what you need for these comparison methods is to know, for example, that you have the series you're using for your comparison series. You have to know what it does, converges or diverges. So some where we know what they do is the geometric series. A r to the n converges when the magnitude of the common ratio is less than 1, and it diverges if the r is greater than 1. About the p-series, which we talked about last week,